Hello. In this video, we will be looking at the controller port of the NES. We will learn how to add controller support to an emulator, and also be able to write programs that use it. By the end of this episode, you should be able to build something like this. This video is part of a series on building an NES emulator. In case you're new here, I'll leave a link to the first video in this series. Before we jump in and look at the specifics of the standard NES controller, let's take a look at the controller port that is used on the system. The NES features a pretty iconic controller, but what some people don't realize is that the system was actually designed to support a wealth of other peripherals. This led to a fairly generic design for the controller port, so that it could support controllers besides the traditional D-pad plus buttons. Here is what the port looks like on the NES. Note that the Famicom has a much larger port and slightly different wiring. I'll be focusing on the NES connector in this video. Now that we know what the connector looks like, let's take a look at the pinout so we know the significance of each of these pins. We have here standard ground and 5 volts for power, but the interesting connections are the clock, out, and D lines. The clock signal suggests timing. Since the NES wanted to support a wide variety of hardware, this connector is designed to read bits serially, or 1 bit at a time. The standard NES controller accomplishes this using a shift register. A shift register can be thought of as essentially storing a certain number of bits. The register can then be shifted, exposing a different bit at a time on its output. After shifting through all 8 positions, an 8-bit shift register is empty and returns meaningless data. Now that we know how the controller port works, let's take a look at the standard NES controller. Here we have a D-pad, 2 sort of menu buttons, and 2 primary buttons, A and B. This makes exactly 8 buttons. Fortunately, this aligns nicely with using an 8-bit shift register and connecting it to the controller port. This means that in order to read the state of the buttons on the controller, software needs to save or latch the state of the controller, and then shift the register until all the button bits have been read out. Now that we know what we want to accomplish, let's see the details of how software accomplishes this using just a few MMIO registers. First, the controller state needs to be stored in the shift register. The shift register has a pin called strobe, which, when set to high, stores the current value in the register. As long as the strobe signal is high, reading from the shift register will continually read the first button. After setting the strobe signal low, the shift register will hold its previous state and change only when it is requested to shift. This leads us to the first MMIO register. The strobe signal is controlled via a register at address hex 4016. Only 1 bit is used, and it is in the first place, or the least significant bit. So writing a 0 here sets 4016 to lower the strobe, and setting 1 here tells it to raise the strobe. After setting and releasing the strobe signal, the shift register is loaded with the state of all 8 controller buttons. Once the state of all the buttons is stored in the register, each of these bits can be read out one at a time. These are communicated via bit 1 of either hex 4016 or hex 4017 when reading. Player 1 is from that first address and player 2 is from that second address. Even though the state of the controller is read from separate addresses, both controllers share the strobe from writing to 4016. Since controller bits are returned one at a time, how do we know which is which? The shift register will always return the buttons in the following order. First, A, then B, then select, then start, then up, down, left, and right, in that order. And that's actually all you need to know in order to support the standard NES controller, whether you are building an emulator yourself or writing your own games for the system. Let's go ahead and build a program that will let us test the controller. It should let us know which buttons are pressed at any point in time. This can help us check our understanding of the controller port, and also help test that the controls actually work if we are building an emulator. Our program will read the state of the controller during a VBlank, and then use sprites to display which of the buttons are pressed. In case you haven't seen the sprites or DMA article, I'll leave a link in the corner. This snippet of code demonstrates the key part of the interrupt handler, which is actually responsible for interacting with the controller port. Just like when we used OEM DMA in a previous episode, this code works by keeping a copy of the desired sprite state in memory, and then uses a DMA to copy it all into OEM. So here we have a loop called button update. It reads from the controller port and then ends this with 1 so that we only have the 1 bit, which will give us either a 0 if the button is not pressed or a 1 if it is pressed. And due to design in the rest of the program, which I will link in the description, The palettes are set up such that palette 0 kind of blends in with the background, and palette 1 is the highlighted state. This means that we can use the controller bit that we've used as the palette directly, which makes the code a little simpler. We go ahead and write this palette into the attribute slot of the OEM data, and then we add 4, which is the number of bytes per OEM slot, so that we move from pointing to the attribute position for one sprite to pointing to the attribute position for the next sprite. And then we decrease x, which tells us which sprite we are dealing with at a given point in time, and we loop. And this loop continues until x finally hits 0, which means we have handled all 8 buttons. And that's actually it for the core controller piece of the code. As I mentioned earlier, the full code is available on my site, which I will leave a link to in the video description. If you run the code, it should look something like this. And you can see that as you press buttons, the various sprites kind of light up, and it should also support pressing multiple buttons at once because the NES does as well. And that's it for the controller. Hope you enjoyed the video. Next up, we'll be taking a look at how sound works on the NES. Hope you liked the video. If you did, please consider liking and subscribing, and if you know others that might appreciate this content, sharing helps even more. That's all for now. See you on the next one.